It doesn't matter what the noise is. Okay, so my people leaving me, be stealthy ninjas on your way out. Please put your homework in the box. And then everyone else, yes, the answer is D, because you have, oh, yes. And there's more to that. Okay, so note to self, you guys should realize that if you have a 1 times 10 to the negative 7th molarity of these two ions, that is equal to each other. 1, that's going to tell you it's likely neutral of pH 7. Also, if you have 1 times 10 to the negative 7th of one of those ions and you multiply that by the other ion, 1 times 10 to the negative 7th, what's 1 times 10 to the negative 7th squared? Anybody? What is that? 1 times 10 to the negative 14. Thank you. So whenever you take your exponents, when you multiply them, you have to add them. So that's negative 7 plus negative 7 is negative 4, negative 14. Brady, what's your number? Thank you. So does this number seem familiar? Yes, that's the concentration, or that's what the constant is when you take your hydrogen ion and your hydroxide ion, you multiply them together. So if you have less, this is the 10 to the negative 8th, if you have less hydroxide, the hydronium is going to have to go up for this constant to be what it should be. So if you have lower amounts of hydroxide and higher amounts of hydronium, what's the pH? Acidic or basic? Acidic, because you have more hydroniums. That's the acidic ion. Vice versa, if you have more hydroxide, you have to have less hydronium for this constant to still be. So if that's true, having more hydroxide means you are basic. Right, so that's understanding how the interplay between ions work out. All right, so now on number, whatever it was on the concept, let me look it up. About the weak acid. We're going to get into this in more detail after, in January. So I just want to give you the basic of how weak acids are so different than strong acids. Strong acids, I give you the concentration, and you plug it into pH. So with a strong acid, you just plug it right into your pH is equal to negative log of the concentration of hydronium. For a weak acid, you have to do something a little different. Give me an example of any weak acid you know. Shout it out. Basically, don't say one of the 6 strong ones. Hydrofluoric, good. Hydrofluoric acid. When it reacts with water, what does it make? That is HOH right there. What do acids do? This guy has an H. What does it have to do with this? Yes, it has to be a donor, right? So Bronsted acids are donors. They are going to be a donor of an H+. Or another definition, Arrhenius' definition, means that acids make what in water? Well, Arrhenius aqueous, so that means I was talking about in water, but what do they make in water? Hydronium. Thank you, whoever said that. Okay, so they make hydronium. So both ways, you're in a good place. So you need to make hydronium. Don't just make up things that you think you've seen before. Make sure to apply in the situation. You have seen acids and bases make salts and water. You have seen salts and waters make acids and bases. But this is water being a product, a reactant, and it's reacting with an acid. So in this case, you need to think about the definitions of acids and bases. Okay, so what does that leave left over? 1 second. What does that leave? Fluoride with a 1- charge. Okay. So one thing you're noting is probably like, what the heck is this SMO? Like, what? We haven't seen that before, or have we? Great. So weak acids, you have to make sure that you put the reversible arrow, because we don't 100% ionize in solution. We will reverse back and reproduce these two over here. So what happens is, like, since it doesn't 100% ionize, you have to kind of think about, well, if it doesn't, how much does ionize? We don't always know. So an example could be like 98% of this stays as is, and only 2% of this is actually going to be ionized. But that's just me giving you some numbers. It could be 5%, it could be 1%, it could be 0.0005%. It just depends. So what we have to do is we have to set up an ice box, which we will do this much more after break. But this is ice, meaning initial, change, and equilibrium. And so what we determine is how much does this ionize at equilibrium, and that's going to be this number down here. So whatever this number is down here, that's truly the H3O plus concentration, which if I have that, how can I find pH? If I have the hydronium ion concentration, how do I find pH? Yeah, negative log. You just use your pH formula. But it's just a little bit harder to get to that for a weak acid. It just takes this journey of plugging in information to an icebox. But eventually we do get the H plus concentration. We just plug it in like normal. But normally you don't have to do that because I'm just straight up give it to you. Okay, so we will get into that a little bit. It's a more advanced application. Yes.
So you have strong acid, you're able to just go straight to calculations.
Mm-hmm. And that's what we've been doing. Mm-hmm.
With weak acid, you have to figure out through the equation what donates using the definitions.
Mm-hmm.
And go through that process there.
Plugging in numbers that I would have to give you. Yep. It's a little bit more elaborate. Kareem? Do you have a hand up? Okay. Another question was number 15. It gave you phosphoric acid, right? Number 15, phosphoric acid, H3O or 3PO4. Make that act like an acid. Tell me what it would produce. Okay, so hydronium, and then that leaves itself as what? Once it's dropped off one of its H pluses. H2PO4, but what charge? -1, because once you lose a plus, you drop down to a negative. So this is the acid, and this is first conjugate base, because it did say conjugate base says, right? Okay, so that means more than one. If you just put one, it's not going to be right. This is one of them. Make it deprotonate again, meaning lose another H. And the charge, because it drops down even further, so it's doubly negative. And then make it deprotonate one more time. PO4 3 minus, because you dropped off the final H, so that's our third conjugate base. This one happens to have 3 because you can, it's a, what's the word for an acid with 3 H's? Triprotic, good. That's a triprotic acid because it has 3 H's, and therefore, since it can deprotonate 1, 2, 3 times, it has 3 conjugate bases as well.
So you can just keep dropping off the H's
Until you're done. Mm-hmm. All right, does that help on questions from your problem set? I will go over the true false with you real fast because I know sometimes that conceptually helps a lot. So I have the key for you right here. Do note I have to correct this as we go, but number 1, sometimes, mark this down as you go. 2, not. 3, not. 4, always. 5, always. 6, always. The way 7 was written was not. I think I maybe fixed that. This is a really high-level key. So 8, never. 9, never. 10, never. 11, sometimes. 12, sometimes. 13, sometimes. 14, never. And 15, sometimes. And you have that right in front of you so you can see your results to see how, and go back and go ahead and do anything that you need to do kind of talk in your groups if you need to about anything conceptual. And there are a couple staplers around the room. I do want you to staple your problem set and your labs. And I just don't know what the staplers are, so bear with me. You want to staple your problem set and your labs. One thing I do not want is your paper copy of your problem set. I only want your responses, not your paper, because that's something I can use and help on.
While you're waiting on me, please proceed with concept 19B. I think you can go in the room.
Yeah. Only because, like I said, we're going to review that much more in depth in January, and I don't think you want to know like all that right now. So write down what you need to there.
All right, one more time. I'm giving you an option to work on concept 19B, and you're going to be stapling your papers. And I don't think there were really any other options. Thanks, guys.
Don't worry about it.
Staple, two dots. Two dots. Thank you. Your lab and concept 19A are in the box. Lab and concept 19A are in the box. It'll be really nice if one person from your table picks them up and put them in the box.
The only thing about my snow globes at work was that everything else messed up. Yeah, the thing from we put too much stuff in it.
Really? Alright, Ian, if you need to be back in your seat as soon as possible, find your notes in the back of your lecture notes from the other segment. Back of the crossword, we are doing notes on the side. Back to the crossword, we're doing notes on the other side.
You checked it like yesterday.
We talked about it.
Because I was down.
Alright guys, back to me. Thank you. My goal is to give you the last 20-ish minutes to work on homework because I thought we were going to get some nails in first period and the whole assembly thing threw everyone off. So we're going to kind of work through titration notes, some examples, and then if you have an opportunity, you'll start the simulation. If not, we'll do it tomorrow. Otherwise, you'll have some time at the end for questions and homework. So a titration is something that we will actually perform. It'll either be tomorrow or it'll be after break. But it's a volumetric analysis of a chemical reaction. It's an acid-base reaction. What do you call an acid-base reaction? Acid plus base. Say again? There's only two types of reactions in this entire unit. Neutralization, right? The other one is called hydrolysis, but it requires not an acid plus a base. It requires salt plus water, right? So we're focusing on the acid-base reaction. So here's the definition of a titration, because I didn't make you do the reading guide, so this is like the definition perspective you need. It's the volumetric analysis of an acid, or I'm just going to say of a neutralization reaction. Okay, so you know that a neutralization reaction is an acid-base reaction. This is on the back side of the notes that you had your lecture notes for. So basically, we have to be able to take the volume of something, but it's also a reaction, and many times these are solutions, like an acid solution plus a base solution. Many times, you guys have seen this in the lab, You see something on the bottle along with the name. What have you been seeing in your solutions to describe the concentration? That could be percent. I'm not a percent kind of person. There are many ways to express concentration. Say again? Molarity, right? M for molarity. So many times you're going to have the molarities given for both of these solutions, but maybe not the volumes given for both. And so in our reactions, we have to measure the volume very specifically. And these guys are called burettes. It's a long, skinny piece of glass, and it's got volume markings on it. So volumes in milliliters. And it's got on the end a little point, and it drops water or drops solution out. It's got a little knob on it, and you twirl the knob. It's called a stopcock. Go ahead and laugh if you need to. Get your giggles out. Okay, we got that out good. So that's stopcock, and this is called a burette as a whole. B-U-R-E-T. And it's an expensive piece of glassware. It's like $120. Yeah, sheesh is right. It's got a lot of very accurate measurements. So the more accurate things are, generally the more pricey they are. So I want to make sure you are the masters at this before we jump into the lab, because you guys are like, oh my gosh, $1 for a test tube? Yeah, can you imagine? I did have somebody break a stopcock one time. It was $65. Okay, so what you're doing is you're adding an acid and a base together. If I start off with an acid, what's the pH generally going to be? Below 7. Give me something maybe a strong acid, more specific. 2 or 1, right? So label your axes as pH and volume of base added. So volume of base added. So as I add, if I start with an acid and I add a base, what's generally going to happen to the pH? It's going to rise. Well, pH is an exponential mathematical relationship, which we briefly talked about with log information. So if you guys probably learned that logs are base 10, right? Yeah. Okay. Log base 10 means that if I have a pH of 1 versus a pH of 3, the difference in concentration is, let's call that 10, where base 10 means it's 10 to the third difference. So this might be a pH concentration of 1,000. So it's not like a linear, it's 1, 2, 3, 4, 5. It's 10, 100, 1,000, 10,000, 100,000, so forth. So what you're going to see on this graph is an exponential kind of curvature to it. So as I add my base, it's going to go up in pH, go up in pH, and it's going to shoot up like this. And then you're going to continue adding base, and then it's actually going to level back out, because you can't just keep going up, right? We actually have to end at 14-ish. So this is about a pH of 1, this is about a pH of 14. And then what we call the point in the middle is it's right between, and it's very specific, okay? So the vertical section of the graph, or this pseudo-vertical section of the graph, has kind of a start to where it gets vertical about right there, and an end to where it's about vertical right there. So if you eyeball it, you get the vertical section. The halfway point of the vertical section we call the equivalence point. The equivalence point is where the moles of acid equals moles of base. So at that point, we have this idea that we've 100% made all of our reactants of acids and bases equal in a mole-to-mole ratio, kind of like a 1-to-1 ratio. And that's going to be important when we write our chemical reactions out as well. So that's called the equivalence point. Well, yesterday you guys learned that we had these fancy chemicals that change color at different pHs. What were those called? Indicators, right? We use this stinky indicator called cabbage juice. There's all this other one that's got in it. What's that one called? Phenolphthalein. So phenolphthalein, right? You guys know what that meme with the little dog is got his mouth way back? You know what I'm talking about? It's mine was Stephen. No one knows him? Thank you, Izzy. Okay, that's what I always think about. Phenolphthalein. Okay, so phenolphthalein will change. Where did I tell you that phenolphthalein will change from clear to bright pink? It says when base, and it was pH 8. Good. So I will tell you that phenolphthalein will start to change pink. This red looks pink, right? You squint your eyes, pink. Okay. So this is the indicator. Phenolphthalein. Okay. And that's going to change at pH equals 8. Well, if I have an acid and base, and let's say they're strong and strong,
Just like you learned with salt hydrolysis, if you have a strong acid and a strong base, they meet in the middle at pH what? 7, right? I will tell you if this is a strong acid, strong base titration, like this curve is labeled here, up here, the equivalence point should be at pH of 7. Okay, so the equivalence point that I just said was moles equals moles. That should be at pH 7. If I use a good indicator, I didn't label this. When the indicator changes color, it's called the end point. Notice how similar those are. End point is when the color changes. Equivalence point is when the moles equals moles. But we really want those very close because I can't see this pH changing. It's clear, 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 clear. Oh my God, it's pink. That's what I see in a titration. So we want to choose our indicator so that they very closely match the end point and the equivalence point. And that's pretty close, right? 7 and 8, that's pretty close. So what you actually see in a situation like this is this. You have a burette, and you're dropping your base, dropping the base, guys, okay, into your flask. Your flask has acid in it, and this is how you'll set up your titration. This right here is going to be pH pretty low, like 1 or 2. As you drop your base, it's slowly getting more basic, more basic, more basic, but you can't see that until you see this little pink dot. That's probably about pH 8-ish, right? And then you put one more half drop in there and the thing turns like pale pink. That is a good endpoint. That is when you're supposed to stop titrating. But occasionally, people will be like, I think I can put one more in there. It's like, it's so close, I'm going to put one more. And it turns magenta, and I say, oh, you've overshot, you've gone too far, start over. So this is actually what we don't want. We don't want to turn 100% pink because we want to stop the equivalence point. So that's actually too far. But you'll see this in the lab when you actually do it. That's using the indicator, what again? Phenolphthalein, right. So we have different indicators, but this one's the one we generally use. So that's this is kind of what the curve is indicating. As your milliliters of base are added, the pH is changing, that's what it looks like. That's for a strong acid, strong base combination. Look at this blue one up here. Can you guys see the differences between the weak and the strong acid? What do you notice about, first off, where the weak acid starts its pH? Right, it's starting at about 3 because that's a weaker base than this strong one, acid, because it's a stronger acid down at 1. What else do you notice is different? What approximately is its equivalence point? Maybe 8-ish, right? So this is a halfway point, so maybe like 8.5 or so, where the red one, which is the strong combination, is more at pH 7. So you should be able to identify from a curve like that what the combination includes. Just is it strong weight base, strong acid, or is it weak acid, strong base, and so forth. So this blue one is a weak acid plus strong base combination, which makes an equivalence point that's higher than 7. So what would it look like if you had a weak base, strong acid? So pH point would be, or equivalence point would be under 7. What if I started you off in a different place? You know what? I think I got it backwards, sorry. If I did this right, give me a second, I want to actually find that curve. I've got about 100 pictures on this one particular one. Well, you know, maybe it's not that important. Oh, it's right here. It's right at the bottom. Sorry, I was like, I thought I had a separate slide. All right, so look at this one. Look at the pink curve. What do you notice? Starts off. Is that strong? It's at like an 11 versus like a 14. Well, I'll tell you, ammonia, NH3, is that one of your 8 strong bases? So it's actually a weak base. Okay, so that's a weak base, and it starts off at about 11 versus like a 12, 13, 14. And then where's the equivalence point here?
3.
So you're looking between the, how do you find the equivalence point? Right in between the vertical section here. That's vertical about there. That's about a 5-ish, okay? So that pH of 5 at the equivalence point is telling you I'm a combination of wet and wet. Weak base and a strong acid, good. And that acid is hydrobromic acid, HBr, hydrobromic.
Give me a thumbs up if you can kind of see the differences in those curves to tell the combinations. I'll work with that some more. I'm going to work with that some more. But I'm going to wait until we do calculations. Yeah? Yes, and it has its other characteristics. Actually, no, it's a even weaker base. It's actually even weaker base, but it's still with a strong acid because the strong acid is labeled here as HBr. So it still ends at the same place, which is also helpful to indicate that as well. These can get pretty advanced, and I'm only just giving you the brief of it for now. All right, so let's go back to calculations. This is, oh, not that. This is where you kind of we just picked up on our notes here. I will get to this in a second. This is more like teaching you the steps where I think an example can teach you the steps. We'll go back to this. So I want you guys first to read the question that's on your, this thing is so unloved. Okay, read the question on your paper, which is up here, and write the reaction down that stands out to you, the chemical reaction. Well, it does, but we're not going to do that right now. So I want you to write out the chemical reaction, meaning the acid and base reacting to form a product. Okay, I think you've had enough time to do that. Give me the acid. Give me the acid. HBr and the base. Sodium hydroxide and the salt. Sodium bromide, Na1 plus Br1 minus, crisscross, you're done. And the final? HOH as in water. Good. Balanced? Yes? Nay? Yes, it is balanced. Okay, so the first step on these kinds of problems, you have to write out the balanced chemical. Second thing, you must identify the titrant and the analyte. Now that information I maybe didn't state earlier, but you have this picture, and I'll go back to the picture first. Picture, where's it at? Here we go. Okay, whatever's in the burette generally is going to be called the titrant because you are titrating with it. So the titrant is the thing, you know, both the molarity, so you know the moles per liter, which is what molarity is, and you know the volume for. It also has another name, either titrant or it's called the known, because you know everything about it. You know the molarity and the volume. That's pretty easy. So the one that you're analyzing is going to be in the flask most likely. It's called the unknown or the analyte because you're analyzing the analyte. And it will either have the molarity known, molarity, M, or the volume. It won't have both. That'll be the question. That'll be the thing you're looking for at the end of your math that you set up to solve this problem. So we're jumping back into stoichiometry, where you take your information about one, you multiply them by each other. You can use a mole-mole ratio because we have a chemical reaction, and we'll solve for something we don't know. So, of this situation, who is the known? Because you know what about it? The molarity and volume. So, underneath sodium hydroxide, I'm just going to write my information out. 20.05 milliliters and 0.1819 molar. What do you know about the acid? Do you know the what? The volume of the solution. What do you not know? The molarity, right? So M is our question. So now when you start the problem, you must start with the thing you know everything about, which is the titrant. And you'll get to the end and you'll utilize information regarding the analyte. So what you'll do is take your information and multiply it together. However, what's molarity one more time? Moles per
liters, right? Molarity is moles per liter. So you'll notice I'm in milliliters. I can't use milliliters. What do I have to do with that first? How do I convert that to liters? Do I need to do the whole times 1,000 thing, or can I just move the decimal back 3 places? Is that fine? Okay, so 1, 2, 3, so that's 0.02005 liters of solution for the sodium hydroxide. Multiply that by the molarity, which in this case is 0.1819 moles, and that's of sodium hydroxide. I'm actually going to label that. Divided by its liter, because that's what molarity is established to be. So when I do this, what cancels? Liters cancels. Okay, one part of my goal is accomplished. I'm now in moles of sodium hydroxide. Notice in the end I want to get to molarity of hydrobromic acid. I'm not done yet. Don't calculate just yet. So at this point, nobody cares about the base. I want to get rid of the base, and I want to get to the acid. Well, how do I relate the acid and the base? Mole ratio, right? There's a 1-to-1 mole ratio up here. That's the only way you can relate two things through a reaction. So in this case, there's 1 mole of HBr for every 1 mole of sodium hydroxide. So this cancellation process shows me that you've transitioned from one thing to the other. So moles of sodium hydroxide will cancel because it's on top and bottom. Say again? Okay. So then I get to moles of HBr. So one more time. What's molarity? Moles or liters? Am I at moles? Yes. Either I can go here, say equals moles, get the moles, separately divide by liters, or what's the same thing as dividing? What's the opposite of, hold on. What's the same thing as dividing? Multiplying by the reciprocal, right? So I'm going to multiply by the reciprocal. So, or 1 over, what's the volume of the acid? You say 20 milliliters, and I'm looking for liters because it's in molar, right? Moles per liter. So that's 0.0200 liters. What units remain? What units are left? Moles of HBr and liters. That's molar, right? Okay, calculate. Calculate. There are a number of calculators in the baskets. Just check those two. Wait, what? Continue to the next problem if you're waiting. Yeah. She's thinking it. Alright guys, and I think you've had enough time to calculate. I'm trying to keep you focused here. I know we're towards the end of the year and you're like, I just don't want to do chemistry, but my goal is to make you successful on your final exam because it is 25% of your grade. You will likely see a titration or an example of a titration on your exam. So when you get to the point where you're calculating, I think that if you follow these 3 steps, really, you're fine. Occasionally, the final result's not asking for molarity, so we chose to go to molarity because the question asked us that. We took moles, we divide by liters. If it said find grams, instead of going to liters with this blue stuff here, what would you do with your moles? Convert to grams. What if it said find the volume required? Well, it likely would have given you molarity. Remember, molarity is moles per liter. That's a conversion factor, right? Can't you flip conversion factors? Yeah, you can flip that, and if you put moles on bottom down here, what would cancel? Moles. What would be on top? Liters. So you have flexibility on that last step depending on what the question's actually asking. And you can see that kind of step-by-step process up here. That's why I didn't want to go here yet, because it depends on what's asking of you. And that's on your paper as well. Let me halt there. You guys do this one for yourself. Work in your teams, but please stay on task. I shouldn't have to ask that. You got this.
You're going to see the rest of these, but I'm giving you guys some time.
You have the equation, so when you first plug in the thing for the time, or you just write it out. So you're trying to find clarity. The analytic it's just you have to clarity. So you just convert it.
Jacob, you know how to solve this, man? Okay. If you guys are waiting on me, don't proceed. You have more examples. You are finishing the lecture in the 1 through 3. But I want to help you on the ones you need, so it would behoove you to look at those so you can ask me the ones you need. Thank you. When do you use it?
I'm getting ready to.
Oh.
So this is almost going to solve an alternate way to show people who would like to do it that way. So this is your moles of acid, right? And you divide at the end by your volume of acid. 0.5.
So that would be the same as
It's still molarity, right? Yep, because that's what I want to show you, that you can do both ways, you still get the same answer. 0.8. Joey, would you get 0.823? 32? Something like that. Alright guys, so look on the board quickly for me for especially number 2, and I solved it a slightly different way at the end, just so if you were more comfortable one way or the other. So after you took your standard, which is your... I'll wait for 1 second, thank you. After you took your standard, which was your known, and you plugged in your moles, or your molarity times your volume, and then additionally you plugged in your mole ratio, you got some moles. And if you like the multi-reciprocal, do that at the end if you wish. If not, I divided by liters after I got moles to get molarity, so 0.832 molar of acetic acid. So I'm going to leave that there, but you guys can tell me which other one you want me to do after you proceed.
Yeah, too. Because like we haven't found the mold yet, so like we're looking for the mold. Usually go for
Do you just like do it like normal process, or do you have to do something different? Does it give you two substances?
It does. Oxygen hydroxide and HCl.
Oh. HCl. I thought it was like saying that's like So two in front of the hydrofluoric acid and the plus 2H.
Hydronium? Most of the time, except for bases that have 2 hydroxide atoms. So what do you have to do?
So if bases have 2 hydroxides,
Oh, I just want to count. No, I know down
and then you can plug in. Katie, I'll be there in a second. Katie, I'll be there in a second. Proceed. In your pH formula. Not in your conversions, just in your pH formula. Just in your pH formula. Yeah. Sorry, when you say conversion, I was thinking titrations.
Did you make sure you did the mole ratio? That's what goes on top of the molar decrease. That's what goes on top of the yeah, and then you find the mole. You guys are supposed to mole and then you're trying to find the mole.
Yeah, I got a 1.5. I'm doing your work for this next one. Yeah? It's not. It's not for me. Alright, I think you guys have had enough time to proceed. If I had a quiz on this right now, some of you guys would be awesome and some of you guys wouldn't. Please don't waste your time. Number 3, you should have seen, oh, it's not beautiful, but it's okay. There's a 2 ratio. Shh. There's a 2 ratio, 1 to 2 ratio. Don't judge, it's not that bad. But liters times your molarity of your HCl, 1 to 2 ratio, that influenced that pretty significantly. After you got your divided by your liters, you should have gotten your strontium hydroxide concentration to be what here? Well, hold on, but what's the strontium hydroxide concentration? 0.121? Something like that, okay? But 0.1215? Oh, sorry, I heard another one. Got it, man, I got it. Okay, this is strontium hydroxide. But strontium hydroxide is one of those dibasic bases that make double the hydroxides when they ionize. So what's the hydroxide concentration? 2.5. And that's what you plug into your concentrate. I mean, that's the POH that you'll get, and then you can get pH from there. You guys are doing 1 through 3 on the other side, and after that, you can go ahead and finish up as much as you can of problems at 19B. That way, you guys have time to class ask me questions. Thank you. How much do you always double it? Only the 3 strong bases that are heavily dibasic. Strontium, calcium, and barium hydroxide. Oh,
I don't know if it's correctly, but technically yes.
She said do the
Just now. And it's not
Oh yeah, that's good. There's 3/4 minus.
And then you have to multiply it in the class with all the because like that's what I can do hydroxide.
If you move on to the chemistry line,